Alright guys, so in this video we are going to introduce the polar plane or the polar coordinate system. And we're going to say that the polar coordinate system is an alternate way for us to define a point's position on the plane. Now the way that we're most used to defining a point's position is with the Cartesian coordinate system or the xy axis. And here we define a point's position by its vertical and horizontal displacement from the origin, right, which is where the x-axis and y-axis meet. So right here, if we've got some point on our plane, let's say this point right here, we would say that this point has some horizontal displacement, we'll call A, which we measure on the x-axis, and some vertical displacement we'll call B, which we measure on the y-axis. And of course, the x value and y value come together to give us the ordered pair AB, which give us the position of our point with respect to the origin. Sometimes xy coordinates are called rectangular coordinates, and that's because the horizontal and vertical displacement can make a rectangle with the origin, right? So in the textbook you'll hear about an ordered pair xy defined as rectangular coordinates. Now with the polar plane, what we're doing is we are defining a point's position with a rotation from standard position in the direction of the point, and then a direct distance to the point, right? So looking at this point right here, we would say that the polar coordinates that define the point would first be a rotation in the direction of the point, and then a direct distance to the point. We call, of course, that rotation some angle theta, and we're saying that the direct distance is going to be a length which we define as r. And the polar coordinates are going to be r theta. So right here what we're going to do is get used to our polar plane. We're going to go through and plot some points and talk about some vocabulary. And then in our lesson on Wednesday, we're going to talk a little bit more about graphing functions on the polar plane. So right here, we say that the pole we define as the origin, and that is basically the ordered pair 0, 0 on the xy axis. We say that the polar axis is the positive x-axis, and we define that as the polar axis because, of course, that's where all our rotations are going to start from when we rotate from standard position. Ordered pairs are defined as r theta, where r is the direct distance and theta is the directed angle. In general, right here, we've got a point 3 2/3 pi, where we've got 2/3 pi as the direction that the point is located in as a rotation from standard position, and 3 is the direct distance to the point from that rotation. So right here we've got a polar plane represented where we've got sort of rings that go out from the origin in increments of 1 unit. So we have all the rotations on the unit circle except for the half quadrant rotations. So that would be the rotations that would be either increments of pi over 4 or 45 degrees. So right here, this is a 6th pi, that is a 3rd pi, and if we're looking at our rotation theta as 2/3 pi, that would be the rotation that takes us to our first stop in the second quadrant, right? So that's the direction our point is located in. Now right here we would say that the r value is going to be the distance from the origin in that direction. So basically right here we would say we would go out a length of 3 in the direction of 2/3 pi to our point. So I'm going to count out units with these rings. We would go 1, 2, and that right there is the point 3 2/3 pi on the polar plane. Now, one thing I want to talk about really quickly right here is the polar plane and the Cartesian coordinate system of the xy axis are just two different ways of talking about a point's position. Really, we're talking about a point on the plane, right? And the origin is just our perspective of where we start defining that point. So in general, it's not like this point right here that we're seeing is a different point than it would be on the xy axis. We're just defining this point with a different way to give us its position, right? From the origin, which is of course either 0, 0 on the xy axis or the pole on the polar plane. Okay, so let's take a look at 2 more points here. The next point we want to look at is the point 1, negative pi over 6. And so right here, what we're basically saying is that negative pi over 6 is going to be a rotation down into the fourth quadrant, and then we're saying that our point is going to be a length 1 unit away in that direction of pi over 6. So if we're plotting this point, we would say we rotate down to that first stop in the fourth quadrant, and then we would go out a length of 1 in that direction. Now right here, I'm drawing the angle that we're seeing right here, but in general, you wouldn't really draw that angle in. You would have your polar plane represented in this way where you could sort of see the angles more clearly, and you would just sort of plot the point the way you would on the XY axis when you get more comfortable with the polar plane of the polar coordinate system. Okay, so with our next point, we've got something more interesting. Here we have a negative r value, right? Our theta is in degrees. So right here, what we're saying is, what we're going to do first is rotate to 225 degrees, which is a rotation that is a half quadrant rotation into the third quadrant. So right here, we rotate all the way around to 225 degrees. And then right here, with a negative r value, we're saying that instead of going forward into the third quadrant, because our r value is negative, we're actually going to go backwards into the first quadrant. So a negative r value actually means that we're going to be going in the opposite direction that our angle is telling us. So right here, we're going to go 3 units backwards to 3. And right here, this is the point, negative 3, 225 degrees. So right here on our next page, we've got some points for you to plot, and then we're going to answer some questions about points on the polar plane. So why don't you guys go ahead and pause the video here, and we'll come back and look at this work in a second. All right, guys, so right here with our first point for 3/2 pi, we rotate to 3/2 pi, and then we go a distance of 4 down the y-axis, so 1, 2, 3, 4, and that gives us our point right there for 3/2 pi. With our second point, we have a rotation that is 150 degrees, and then we have an r value of -2. So we'll rotate that 150 degrees, which is all but 30 degrees of a half rotation. And then right here, we're going to go in the opposite direction, which will take us 2 units backwards into the fourth quadrant. Right here with our last ordered pair, we've got 3 and then 8/3 pi. So 8/3 pi is actually more than a full rotation. 8/3 pi is actually 2 and 2/3 pi. So right here we go all the way around, and then we go an additional 2/3 pi past the full rotation, which takes us to the first stop in the second quadrant. And then, of course, we're looking to go a length of 3 units in that direction. So we would count out 1, 2, and then 3. And that is the point 3 8/3 pi. All right, guys, so now what we want to do is ask ourselves some questions about our polar coordinates. And the first question we're going to ask ourselves is, will each pair of polar coordinates define a unique point? Really what we're saying here is there a way for us to interpret our polar coordinates so that we wouldn't get just one point or a unique point? And if we think about it, when we're rotating in some direction, right, and then going a distance r in that direction, either forwards or backwards, really we're always going to end up at the same point, a unique point. And so in general right here, what we can say is that each pair of polar coordinates will define one unique point. There's only one way for us to interpret our polar coordinates to get to a position on the polar plane. Our next question is, will each point be defined by a unique pair of polar coordinates? And this is a more interesting question. Right here what we're asking is, are there some other pairs of polar coordinates that will take us to the given points that were defined here? And if we look at our last example, in our example C right here, what we're seeing is the same point that we plotted on the first page with the ordered pair 3, 2/3 pi. So what we're seeing here is if we have the same r value, then any coterminal angle will basically take us to the same point, right? We can also think about what would happen if we had the negative of an r value. So right here, if we've got -2, if we take a look at what would happen if we had an r value of 2 and let's say a rotation of 330 degrees, what we can see here is that rotation of 330 degrees is going to be a rotation that is all but 30 degrees of a full rotation, and then that direction of positive 2 is going to take us 2 units forward to the same point, right? So really what we're looking at is 2 different ways in which our polar coordinates could be defining the exact same point. And in general, what we can say is if we want to come up with all of the polar coordinates that will define a point, we'll say the generic point r theta, we can say that if we have the same r value, any coterminal angle to theta, which could be defined as theta plus 2k pi, where k is an element of the integers, will take us to the same point. So these two guys are defining the same point on the polar plane. Similarly, we can say that if we have a negative r value, a rotation that takes us in the opposite direction, so we could say theta plus pi, will also take us to the same point as r theta. Now right here, we also have to take into consideration all coterminal angles of this angle right here, theta plus pi. So we would have to say 2 plus 2k pi here as well. In general, right here, if we factor pi out of these last 2 terms, what we're going to end up with then is a negative r, and then theta plus, right here we would have 2k plus 1 pi, which is basically an odd increment of pi, which is a rotation that will take us in the opposite direction from our theta. So right here, these 2 sets of polar coordinates define the same point as r theta. Now, what we're going to do next is talk about ways in which we can convert our polar coordinates to rectangular coordinates and our rectangular coordinates to polar coordinates. And what we're going to say here is that we can convert from one pair of coordinates to the other with vectors, right? So in general, right here, what we want to think is the vector is basically a way of defining the action of getting to the point when we extend that vector from the origin. So right here, I've got a point defined with polar coordinates, and we want to convert those polar coordinates to rectangular coordinates. We're going to extend a vector then from the origin to our point, right? And right here, the polar coordinates are really defining the magnitude and the direction of our vector. That r is actually the magnitude, and the theta is the direction of the vector. So right here, with the r being the magnitude and theta being the direction, we can basically say that that would be one way to define the vector. But the second way of defining the vector is with component form, right? And component form basically defines the vector with its horizontal and vertical change, right? So right here, we could say that with a horizontal change of x and a vertical change of y, component form would then be xy. And when we extend a vector from the origin, component form also gives us the x and y value for the ordered pair at the end of our vector. So right here, what we can say is, if we go ahead and take the direction of our vector and the magnitude r, we can determine our component form. So right here, we would say that a unit vector extending in the direction of our vector xy would be cosine of 120 degrees, sine of 120 degrees. And if we multiply that by the scalar, that is the r value of 3, then right here we have component form as 3 cosine of 120 degrees, 3 sine of 120 degrees. And this gives us component form as approximately negative 1.5, 2.6. Now that 2.6 isn't an exact number, so we have to say approximately. But in general, right here, what we've done is come up with the approximate x and y value that would define our point. So in general, right here, we can say that for the polar pair, 3 120 degrees, we have the approximate corresponding rectangular coordinates, negative 1.5, 2.6. Similarly, when we are going from rectangular coordinates to polar coordinates, we're going to use vectors there as well. And in general, we'll say that the magnitude of our vector is going to be the r value, and the direction of our vector is going to be the theta value for our polar coordinates. So right here, when I'm extending a vector from the origin to my ordered pair that is in rectangular coordinates, I know that the x value at the head is the horizontal component of the vector, and the y value is the vertical component. So we've got the vector 3, 2 there. Now from there, basically what I can say is if I want to determine the direction of that vector, which would also be the directed angle, or the theta for our polar coordinates, then right here I would say that that would be inverse tan of the vertical component 2 divided by the horizontal component 3, and that gives us approximately 33.7 degrees. So right here, that is the theta for our ordered pair with our polar coordinates. Similarly, we can say magnitude is going to be the r value. So right here, when we evaluate the magnitude of our vector 3, 2, we get 3 squared, which is 9, plus 2 squared, which is 4. So that gives us the square root of 13 as the magnitude. And right here we can say that for the rectangular coordinates 3, 2, we have approximate polar coordinates of, right here, square root of 13, 33.7 degrees. And we have to say approximately because I basically rounded that 33.7 degrees. So, all right, guys, so we're going to let you guys try a couple of these. We're going to have you convert polar coordinates to rectangular coordinates, and then right here, down here in our second example, we are converting rectangular coordinates to polar coordinates. The thing we want to take note of here is because we're going to extend our vector into the second quadrant, right here we want to remember that it's not just inverse tan of the vertical component divided by the horizontal component. We also have to add 180 degrees to get that directed angle, or that theta, for our polar ordered pair. All right, guys, so we're going to pause the video here and let you guys give this one a shot. All right, guys, so with our first example, we extend that vector from the origin, and right here, that vector has a magnitude of 4 and is headed in the direction 240 degrees. So right here, when we put this in component form, we have the horizontal component as 4 cosine 240 degrees and the vertical component as 4 sine of 240 degrees. When we evaluate that, we get approximately -2, -3.46. So we can say that the polar coordinates corresponding rectangular coordinate would be -2, -3.46. So that's our first one. And when we're going from rectangular coordinates to polar coordinates, we again extend that vector from the origin. And right here, that means that the direction theta is going to be the direction of the vector. So right here, evaluating inverse tan of the vertical component divided by the horizontal component plus 180 gives us 116.57 degrees. And right here we can say that the magnitude of the vector is going to give us the r value, or the distance we have to go in that direction to get to that point. Right here we get that magnitude as square root of 20, and so right here we can say that the corresponding point to -2, 4 is approximately square root of 20, 116.57 degrees. All right, guys.